We're continuing our series on induction motors. What are we talking about this time?
Well, I think we're going to dive into the torque curve and why induction motors stall as they get close to their peak horsepower. And that's a good subject for today.
What's the opportunity here?
Understanding how an induction motor works in more and more detail helps you be a better designer and understand how to apply what you know to making these induction motors function properly.
You haven't talked about the torque curve of an induction motor. Is that related to stall?
Yes, the torque curve of an induction motor is interesting and convenient. First of all, when the motor starts, it basically looks like a shorted transformer. And we're going to talk about inrush current in another episode. But a shorted transformer basically looks like a big inductive load. So all the current going in is reactive. And it does no work. That's what reactive power is. It's imaginary and it doesn't do anything. So to begin with, the torque is very low. It's not zero, but it's low. And it's enough to get the motor started. But if you have a heavy load at the start, you'll never get the induction motor running. But as it comes up to speed, the current starts to turn more real. In other words, it's doing work. And it will eventually, as the speed goes up, it'll reach a maximum where it begins to saturate the iron in the motor. And once you start to saturate the iron in the motor, you get more current, but you don't get a bigger magnetic field, which means you don't get more torque. So at that point, then the motor collapses. And that is the life of an induction motor. Now, the good news is that most of the mechanical loads in the real world pretty much follow the curve of an induction motor. For example, a fan, when you start it, needs a little bit of power to get it going, but there's no real load on the fan until it is moving fast because the air is not moving fast, so it's not doing any work. But as the fan gets moving faster, it needs more torque, and the induction motor is very conveniently able to provide more torque as the speed goes up. Same for pumps. As pumps move faster, they need more energy, more horsepower to rotate, and the induction motor is a perfect match for that situation. You just have to make sure you don't go past the collapse point where the fields are saturated and the magnetic current, the additional load doesn't actually produce any more torque.
How does that compare to the DC motors we were talking about before?
Well, DC motors are a whole nother subject, but the fact is a DC motor has its highest torque at zero speed. And if you own a Tesla, you know that coming off the line at a stoplight, you can beat any car because you've got the most torque coming off the line. And that's useful for elevators and all kinds of things that need to have a lot of torque when they're barely moving. But fortunately, induction motors are a great fit for almost everything else that starts out slow and has more load as it gets faster.
Explain why the torque curve looks like it does.
Well, again, the textbooks say it's all about the reactive component of the current at the start when the rotor's turning slowly. And that's a technical answer. It's like, how does an atom bomb work? Well, it's E equals mc squared, and therefore everybody could build a bomb. Not true. So knowing that it's the reactive power doesn't really help you understand much other than the magnetic fields are just not doing any work that's useful when the motor is moving slowly. And it doesn't start to really have useful interaction until it almost is up to full speed, so that the difference between the rotating field on the stator and the speed of the rotor are almost the same, and we call it the slip frequency.
What's the solution to a motor that stalls?
Well, as we described, the motor stalls because the iron becomes saturated for the amount of current that's flowing, and you cannot get any more magnetic field. So the answer is add more iron. And that's how you make a bigger horsepower motor. You just make it heavier and heavier and heavier as you go up. And there's no shortcut to that. It just takes more iron to make a higher horsepower motor, which is why they weigh more as the horsepower goes up.
Is there anything being done to make motors lighter and still have high horsepower?
Well, motors are a very mature industry. They've been designing and refining motors for 100 years. And so they're pretty close to optimum right now. If it's absolutely important, you can use better wire, you can use better materials in the core and the stator and the rotor. You can use thinner insulation. There are things that can be done, but right now the typical motor is a pretty good blend of cost effectiveness between the price of building the motor and the amount of gain that you would get in efficiency by making it, well, more expensive and more efficient. The codes are driving higher efficiency on motors, however. So there is an incentive to make them more efficient, but there is a price to pay to add the higher quality materials and closer tolerances on spacing, etc.
Let's review what we've talked about today.
Well, basically what we're trying to cover here is the fact that the torque curve on an induction motor starts out low and gains value and torque and horsepower as it gets closer to the slip frequency. And then you're just about at the point where the magnetic material is saturated. And once you go over the saturation, the motor loses any ability to provide torque, and so it collapses. And of course, as it collapses, if you've got load on it, as it collapses, the torque goes down. And so it's an avalanche, okay? The slower it goes, the less torque it has. The less torque it has, the slower it goes. It just keeps dropping and dropping and dropping. And that's why an induction motor collapses after you get to full load.